All right, the first application of limits that we're going to do is one of the major components of any calculus course, and that's derivatives. So let's start off with an intro to these things and sort of give a reason why it came into existence. You might have known that Isaac Newton was an inventor of calculus, and one of the things that he tried to determine was how fast objects were moving at any given time. So let me introduce you to that. So if you drop an object from a height of 100 meters, the height of the object is given by this formula. I don't know why h is not used, probably because we use h for a lot of other things, but usually they'll write s of t, s being the position of the object, t being the time, where that'll be in seconds. This equals negative 4.9 t squared plus 100. Of course, s of t is in meters. And t is in seconds. So how fast was the object going at 2 seconds? So that's my question to you. How fast this may seem strange. I want to know how fast its velocity is right at the moment of 2 seconds. Not around 2 seconds, or not from 2 to 3 seconds or something like that. But nonetheless, that'll be involved. What we do is this. First, let me put it this way. Let's calculate the average velocity for t equals 2 seconds to t equals 3 seconds. So I'm doing an average velocity. Let me review for you what that means. The average velocity, so I'll write it as v sub avg equals the ending speed, or end position, in this case the ending height, minus the start position, divided by the elapsed time. So what I have in this case, t is going from 2 seconds to 3 seconds. So if I could get the position at 3 seconds, subtract the position at 2 seconds, and divide by the elapsed time, well, how much time has elapsed? From 2 to 3, the total difference is, well, I'll write this, 3 minus 2 so we can see where it comes from. 3 seconds minus 2 seconds. The elapsed time will be 1 then. And this will be in meters per second. So I'll calculate these numbers. S of t equals negative 4.9 t squared plus 100. Actually, what I'm going to do is let the calculator do these numbers for me. So let me pull up my graphing calculator. Into y1, you want to make sure that you have the function we're looking for. So I have negative 4.9 x squared plus 100. So t is just not the variable that the calculator uses for this particular part. Now what I want to do is I want to figure out s of 3 and s of 2 and then subtract them. So let's go ahead and do that. S of 3, in case you need to remind yourself, is negative 4.9 times 3 squared plus 100. And what I'll do is I'll set my table to start at 2 and to increment by 1. And now let me go ahead and take a look at these values. So this was, I didn't mean to make it switch here. This was 80.4. Then S of 2 equaled negative 4.9 times 2 squared plus 100, which equals I did them backwards. The 3 was 55.9. And the 2 was 80.4. So to get these numbers up here, I'll just plug them in there. S of 3, that was the 55.9. The S of 2 was 80.4. Of course, the denominator was just 1 second. So, let me see, this is equal to 24.5, negative 24.5 meters per second. I'm not going to leave it at that. I'm actually going to check that out. Let me go back to the home screen. 55.9 minus 80.4. Negative 24.5. So, I know how fast it is on average over the interval. So the way we get this to the, so I get an instantaneous read, is I'm going to next work on a smaller interval than from 2 to 3. Try, how about t equals 2 to t equals 2.5. That way, the average velocity equals s of 2.5 minus s of 2 all over 2.5 minus 2. I'll keep reminding you this is in meters per second. And now, I've already got the number for s of 2. Let me put in the numbers I do know right now. S of 2 I knew to be 80.4. S of 2.5 is very easy to find. All I have to do is change my table set. I still want to start at 2, but this time I'm going to increment by 0.5. That way I'll capture 2.5 in there. And then I'll look at the table values. And what do I get for 2.5? 69.375. And then on the denominator I have 0.5. So for a half-second interval, this is the average speed that we get. So let me do these on the calculator. I think I'd have to put here 69.375 minus 80.4. That's negative 11.025 divided by 0.5. So let me complete it by then dividing by 0.5, and we end up with negative 22. Negative 22.05 meters per second. Now, when it comes to the instantaneous velocity at 2 seconds, notice the average velocity from 2 to 3 was 24.5, the negative indicating you're going downwards and it's dropping. That's why all these are negative. Here, from 2 to 2.5, I register a slightly smaller average velocity. Now, you understand that when you drop an object, and I'm neglecting, this is one of those science experiments where you're neglecting all wind resistance, the shape of the object falls perfectly, like it's round, pretend it's happening in a vacuum, that kind of stuff. So, what happens then is the object will go faster as it falls. So at 2 seconds, it's going to be going slower than over any interval, because at t equals 2 will be the slowest of all the numbers I'm considering, since I'm talking about numbers bigger than 2. Anytime bigger than 2, the object is traveling faster. That's another reason why these numbers are all negative. Well, let me keep going and do this for a while. How about t equals 2 to t equals 2.1? So once again, I'll compute the average velocity, s of 2.1 minus s of 2 all over 2.1 minus 2. And once again, I've already got s of 2 a million times, that's 80.4. Down here is 0.1. And then to get s of 2.1, I'll simply go back to my table, set, and I'll change the increment to 0.1. And I'll look at the table value for 2.1. That is 78.391. And that equals, and once again, use the calculator to help me out here. We have 78.391 minus 80.4. That's negative 2.009. I don't need the calculator for this next step. You ought to remember this yourself. This is negative 20.09 meters per second. So you see, as I decrease these intervals, next I'll go even smaller. So I'll go from t equals 2 to 2.01. What I'm doing is I'm getting closer and closer to the number t. What I'm going to do is, as I keep doing this, I'm going to take the limit of all these processes and allow t to approach 2. But for a while, I want you to see how the numbers are stacking up. In this case, the average velocity on this small interval is s of 2.01 minus s of 2 all over 2.01 minus 2 meters per second. This equals, and once again, we know all the numbers except s of 2.1, that was 80.4. The denominator is easy to do. And now I need is 2.01. So I'm going to go over back to my calculator, and this time I'm simply going to go to the table and increment it to be 0.01. And then what I'll do is I'll look at the table values for 2.01, tell me what it is. Here I get 80. Wish I could have copied that. 80.20351. I might cut this down to 2 or 3 or 4 decimals. Let me go ahead and calculate this new number. Yep, I meant to go to click there. So we go 80.20351 minus 80.4 equals, so I have negative 0. I should have said it out loud before I started going. Negative 0.19649. All over 0.01. Just move the decimal 2 places to the right, and we have negative 19.649 meters per second. So you should feel like you're getting closer to how fast the object is traveling in exactly 2 seconds. Let's do a big jump for the next one. I'm thinking somewhere around 19 meters per second. Let's go from t equals 2 to t equals 2. I usually go 3 decimals, so to ensure 3 decimals, I'll go 4 decimals in my increment here. And let's see what happens there. So once again, the average velocity equals s of 2.0001 minus s of 2 all over 2.0001 minus 2. And as before, I know everything except the first number. So I will go and get that now. And as before, what do I need to increment by? 0.0001. So I will go to my table set and go 0.0001, and then I'll go take a look at my table value. I think I'm going to round to 3 decimal places, so 80.398. So let me go ahead and do this on the calculator. Negative 0.002, 0.0001. Well, I want to move the decimal to the right 4 places. Negative 20 meters per second. Now, what if I told you there's a way to do this without all of these steps? I could have figured out this number without jumping through all of these hoops. If you look, the average velocity is s at the end minus s at the beginning all over time. And I'm not really sure what I'd like to put here, but let's just say we go from t equals 2 until some small increment later. I don't know, let's call it until t equals the number a. I don't know what a is, but I'll let a be some number. So the way this is going to look will be s of a minus s of 2 all over a minus 2. Now if you'll notice, we were going from t equals 2 and a was 3, then t equals 2, a was 2.5, t equals 2, then a was 2.1. We kept shrinking a closer and closer to 2. So if I want the instantaneous velocity, I probably should be looking at the limit. Is that number a is going to 2, s of a minus s of 2 all over a minus 2. I probably should have used t, but I think I'll do that for the next one. So let's put this in. This equals the limit as a goes to 2. And since a is always bigger than 2, let me put a plus up here. A is actually approaching 2 from the right. Let me put in what the formula for s of a was. That was negative 4.9 a squared plus 100. And s of 2 we knew to be 80.4 all over a minus 2. This equals the limit as a goes to 2 from the plus of negative 4.9 a squared plus, it looks like 19.6 over a minus 2. Now, as with any other thing, I'm going to try to plug in a equals 2, and let's see what happens. So I would get negative 4.9 times 2 squared plus 19.6 all over 2 minus 2. This is not looking good. I hope the numerator comes out to be 0. At least then I'll have something to deal with. So negative 4.9 times 4 is 19 points. So we happen to get 0 over 0. So I cannot do this. So what I'm going to have to do then is do the process like we had before. Now, keep in mind this. Since 2 makes both the numerator and denominator 0, we know that this limit as, well, a goes to 2. I should have put a t, but it's okay. A goes to 2 from the positive. We know that a minus 2 is a factor of the numerator and the denominator. The bottom is just a minus 2. Then what's left over here? Let me make the parenthesis bigger. I know I have to start with negative 4.9 a squared not a squared, I just want that. And I have to end with negative or positive 19.6. So that means I must have a minus here, and then 4.2 squared is 4.9a times 2 goes into 19.6, 9.8 times. All right, good. So let's go ahead and cancel the a minus 2's. And we get the limit. So a goes to 2 from the positive. Negative 4.9. This is where I can plug 2 in. And that equals, I should have left that off because that's when I plugged it in. Negative 9.8 minus 9.8, which equals negative 19.6 meters per second. Now, the whole process could have been done for numbers less than 2. Like I could have gone from t equals some number, let's say 1, to t equals 2, t equals 1.5, to t equals 2, t equals 1.9. You get the idea. I can keep doing this and approach the instantaneous velocity from below. So I could consider this the limit. This time I will use a t. T goes to 2 from the left. So that means that we are ending at t equals 2. So we'll have s of 2 minus s of t and 2 minus t. All right, let's throw our numbers in then. This equals the limit as t goes to 2 from the left. S of 2, I believe I did that one, didn't I? S of 2, where was that one? That was negative 80.4, or just 80.4. And then this one, negative 4.9 t squared plus 100 all over 2 minus t. This equals the limit as t goes to 2 from the left. 4.9 t squared, those negatives cancel, minus 19.6 over 2 minus t. Now, since 2 makes the numerator and denominator 0, I know this just by looking at it. I know that t minus 2 has to be a factor of both the numerator and denominator. We can see down there it clearly is. So I know the top must factor as t minus 2 times something. Now since I need to start with a 4.9 t squared, I know this will be 4.9 t. And then I need to end with a negative 19.6. So 19.6 divided by 2 is 9.8. This has to be positive 9.8 all over t minus 2. Now here I can cancel, except be careful. 1 is the negative of the other one. So we put a negative 1 here to indicate that it's that negative. Now I'll put the negative 1 here, and I'm able to substitute in t equals 2. So I get 4.9 times 2 plus 9.8 equals negative 19.6 meters per second, exactly like I had before. So the left and right limits are the same, therefore the limit as t goes to 2, s of t minus s of 2 all over t minus 2 equals negative 19.6 meters per second. Now, this is sort of interesting. If you look back here, I had s of 2 minus s of t, like if t was below 2, but this was switched in the numerator, so, and the denominator was also switched. If you look up here to the previous problem, I had a first, 2 second, a first, 2 second. Now I'll go back to this version, 2 first, t second, 2 first, t second. What happens if, algebraically, if I multiply the numerator by negative 1 and the denominator by negative 1, I will get this expression up here, except there'd be a t instead of the a. Not everything has symmetry like this. But now, one thing, can I come up with a formula? Create a formula. For the velocity, instantaneous velocity, I should use that word, at t equals a seconds. Well, then I'm going to have to do something like this. The limit as t goes to a, s of t minus s of a all over t minus a. Now let me plug in these letters into the various formulas. This is the limit as t goes to a. S of t was negative 4.9 t squared plus 100 minus, now s of a was negative 4.9 a squared plus 100 all over t minus a. Now this is nice. The hundreds cancel out. So I'm left with the limit as t goes to a, negative 4.9 t squared plus 4.9a squared all over t minus a. Now, if you try to plug a in for t, you will, I guarantee you, end up with 0 over 0, and don't do that. So instead, knowing that it's 0 over 0, I know that t minus a must be a factor in the numerator. And I'll make it a little easier on you. I can do this. The limit as t goes to a, I'm going to factor out negative 4.9. That'll leave me with t squared minus a squared all over t minus a. You should recognize that top is a difference of squares, and it factors as t minus a times t plus a all over t minus a. So I can cancel the t minus a's. You knew that had to happen. Now I am permitted to plug in a where there was a t. And so I end up with negative 9.8a. So when a was equal to 2, if you plug that in, you'll get the negative 19.6. In fact, now I can find out the velocity for any time I want. All I got to do is change the value of a. So what was the velocity? I'll call it instantaneous. I'll stop there. Velocity at 3 seconds. So all I have to do then is replace the a with a 3, and that's negative 27 and 2.4, negative 29.4 meters per second. You can do this all day long. The only thing you can't do, I mean, eventually you're going to put in a number that's so big the object has already landed. But what we have here is the notion I was talking about. The thing that I have, the limit as t goes to a, s of t minus s of a all over t minus a. This is called the derivative of s. In fact, not a t. Let me change that to an a. This is the derivative . And the notation is usually said s prime of a. So this gives us, once you calculate this, and it's not, as you can see, the steps we had to go through was no different than anything else we did there. We simply plugged in these numbers. And all I did for this last one was, instead of plugging in numbers, I just let a held their spot. An interesting question should be this. When will the object hit the ground? Well, its height would have to be 0 then. So s of t, the height of the object, would be 0. So let me replace s of t with negative 4.9 t squared plus 100 equals 0. And then I'm going to solve for t. So t squared equals negative 100 divided by negative 4.9. T squared equals 100 over 4.9. It depends on how much you want to get in decimals or something like that, but I'll stick to doing it algebraically if you don't mind. You can rewrite this as 1,000 over 49. So then t would equal plus and minus the square root of 1,000 over 49. The negative is absolutely unnecessary because that would be going back in time, so I'll throw it out. 1,000 is 10 radical 10, or the square root of 49 is 7. That's when it hits the ground. How fast is the object going? When it hits the ground. Let's check my formula out. This right here is my formula. So S prime of A was negative 4.9 times A. So what I want is S prime of 10 radical 10 over 7 and equals negative 4.9 times 10 radical 10 over 7. And at this point, I don't mind getting a decimal for it. Although I wouldn't care if you left it like that. Hey, I can see something interesting here I didn't think about. 10 times 4.9 makes this negative 49 times radical 10 over 7. I'm just playing around algebraically right now. That's the exact. I'm not going to make it, what do you call it, approximately. Let me cancel here and here. So it is traveling at negative 7 radical 10 meters per second the moment it hits the ground. And if I really wanted the decimal for that, I'll just do 7 times square root 10. So negative 22.136. How big is that number actually? Let me see. 10. Radical 10 is a little more than 3, so that's 30 over 7. So it's in the air for somewhere around 4 seconds. Anyways, that's more than enough time for one lecture. We will do many more of these types of examples in the next lecture.